My name is Nima Farzadnia. I'm from the University of Alaska. The previous talk was about freeze and thaw of 3D printing elements, and I was feeling the freeze and thaw from Alaska to California. Anyway, so the thing is that this is what I started when I was a research assistant professor at the University of Tennessee, and still in progress. And now a new PhD student is working on that. They're working with Dr. Zhou, that is already in the session too. So it's about internal curing of 3D printable cementitious composites using superabsorbent polymers. So this is, we did the feasibility study actually, and now more detailed research is going on. Like I said, that this is Reese is working on that. Hopefully next time he's going to come here and present it. I'm presenting on behalf of him, kind of. Well, the thing is that we all know about the problem, one of the major problems with 3D printing, and that is evaporation and drying, which can cause volume stability issues there, okay? So because for conventionally cast concrete, we have formwork, and the thickness, or let's say the width of the sample, is not that high, that evaporation causes a very serious problem, especially with higher water to binder ratios, okay? But when we have lower to water binder ratio, and then we have the kind of like a larger drying surface, definitely we're going to have more evaporation, and we need to think about that. Like you see there, so in 3D printed concrete, the risk of evaporation in different directions. That this can cause higher porosity, and also if the water that is needed for hydration of cement is out, then we would have incomplete hydration. And then we would have weak interfacial bonds, impaired durability, lower strength, and lower volume stability. My previous study actually showed me that SAP, or superabsorbent polymers, are a really good candidate to solve the problem. Superabsorbent polymers are actually cross-linked polyelectrolytes that when they absorb water, they swell, and it takes about some time to release the water into the matrix. And this gradual release of water provides kind of like some functionality that we can use SAP as internal curing agent, as you can see there. And of course, the properties of SAP, the chemical characterization, chemical property of SAP would vary, and this changes the absorption and the desorption capacity of SAP, which should be studied if you want to use that in 3D printing. Again, this is from my previous studies. We figured out that SAP is a very important, it has an important functionality in controlling the evaporation. If we have the same water to binder ratio in concrete, for example, here we have water to binder ratio of 0.22, 0.18, and 0.22, and when we add SAP, actually, it reduces the water to binder ratio, it reduces the evaporation significantly. And this control of evaporation can lead to formation of higher density calcium silicate hydroxide or ultra high density calcium silicate hydroxide. The results are already available in the Cement and Concrete Research Journal. And so I don't want to talk more about that, but we did extensive research using nanoindentation technology to show that how this calcium silicate hydrate can change in density with the distance from SAP. So technically how SAP can help strengthen the calcium silicate hydrate in the mixture. So as continuation of our previous study, and as kind of like applying the advantages of SAP, we thought that this is a good idea to use SAP in the 3D printing. But there are major questions. Number one, how does absorption and desorption capacity, which can change with content size and molecular structure, affect printability of 3D concrete, which is a very important issue for us? How robust is a 3D printable mixture with SAP is, based on the variation in the absorption and desorption? And how does SAP affect mechanical properties and volume stability of the printed concrete? what I'm showing to you, like I said, is a feasibility study, and it only deals with one type of SAP, sodium neutralized acrylic type, with a median size of 450, irregular shape, and we developed our own non-proprietary mixture with a water to binder of a ratio of 0.31 and maximum aggregate size of 650, so it's kind of like a mortar. So this is the first thing that I want to share with you. We measured the absorption and desorption capacity of SAP using T-bag test and also as per ASTM C1761, which is used for lightweight aggregate. And we realized that there's a huge difference in the absorption capacity when we are testing our SAP in water or testing our SAP in a mixture associated with the 3D printable concrete. It's like 10 times the absorption rate decreases. And as you see there, there's another important issue. It's about the time. If we assume that printing open time is about 30 minutes, if you look at those times, you will see that at 10 seconds right after addition of water to SAP or pour solution to SAP, let's say the retention or the water that is retained is about 35 grams of water per every gram of SAP. So it means that your mixture will dry out immediately after 10 seconds. And after 30 minutes, which is about our open time, that water retention goes all the way down to 4 grams per gram of cement. Okay, we have a problem during that time because the first 30 minutes is important for us, and it seems that the SAP sucks down all the water or a lot of the water that we need for flowability and the printability of our mixtures. And about the desorption of what you see on the right, so it has a slow desorption, which is quite similar in water and also the pore solution. And what happens, just like I pulled up one of the numbers there, 24-hour moisture content is like 97%. It means that within 24 hours, SAP still holds its water. And technically, based on previous studies, after the first 48 hours, it starts releasing the water into the matrix, which provides enough water for the hydration of cement. So, but like I said, this affected our flowability. We use ASTM-C 1431 for now, just like a very quick estimation of our flowability and the flow range, and we realized that SAP at different contents, 0.2%, 0.4% of cementitious material, and 0.6% of the cementitious material decreased the flowability to some extent. But of course, this was for the fresh immediately after mixing. But after like 30 minutes, we had more constant values for flowability comparing control sample and the ones with SAP, which is mostly because the hydration of control sample was very quick, but SAP, because of the gradual release, the hydration was kind of like delayed. And the other thing, so we wanted to figure out, okay, what's going on exactly. So we checked we did hydration scanning, and you see the results here. Of course, I have only the results for control 0.2% and 0.4%. And as you see, as we are increasing the amount of SAP, the hydration is decelerating, and it's mostly because there is less available water in the matrix, in the mixture for cement to hydration. So that's one of the reasons that, I can say that flowability was flow of the mixture decreased. And we observed the same effect on the setting time. As you see, we used the penetration test ASTM 403 to measure the setting time at, and you see 500 psi and 4,000 psi as per ASTM are used to tell that what is the initial time and what is the final setting. Okay, initial setting and final setting. And again, you will see that the setting time is being delayed because of incorporation of SAP. And all this, they're kind of like the signs for us that, hey, when we have SAP, we would have some changes in the printability of our mixture, and we have to be worried about that. And one of the concerns is that from zero time to the first 30 minutes, this absorption and desorption can change the printability. So that's one of the things that we have to overcome in this study. And but SAP, this is not from the printed elements. We are now, I mean that the results are out, but I'm not sharing it here. So like the phrase shrinkage, this is like the shrinkage, autogenous shrinkage of the associated mortar to our printable mixtures. And you can see that when we add SAP, what happens is that the autogenous shrinkage is decreasing, and even when we have like 0.6% of SAP, we have a little bit of expansion, which we can say that it can control it can compensate and inhibit the shrinkage in 3D printed concrete. So what we had to do later was to go through the printing of this 3D printable mixture with different parameters. We did the test, like we did extrudability test and also buildability test at the constant, let's say, printing parameters, but different nozzle diameters. For extrudability, we use a 10 millimeter nozzle, and for buildability, we use 20 millimeter nozzle. But the rest, all the printing parameters were the same, were kept constant. So the first issue was about the extrudability. As you see, number one shows the control samples. As we are increasing the content of SAP, our bits are becoming kind of like narrower, and this is because our mixture is kind of like drier, and so it can be extruded well, although we don't have any kind of like cut or break in our bits. So this is one of the issues that we have to be worried about or concerned about when we are using SAP. And the other problem that you see that this is the process of printing. We just use a small sample, like with 8 layers and like 10 inches of let's say the length, and we realized that there is an issue. The issue was that when we printed with higher content of SAP, like 0.4% and 0.6%, the top layers were like narrow because the mixture was kind of like dry, but the lower layers were flat. And it caused kind of like the average height to go down when we have 0.4% and 0.6% of SAP, all this exactly in the contrary to 0.2%. And the reason is kind of like here. The reason is that when we added more SAP, we needed more superplasticizer. So we added more viscosity modifying agent. The fact is that superplasticizer kind of like lowers the viscosity. It helps with the extrusion. It helps with the flow, but it's not really in favor of the buildability. So this is one of the concerns that we have now. Okay, so how to kind of like manage all this? But the rest, for example, about compressive strength, and you will see that the printed structure, the printed concrete, it goes as high as like 75 to 80 megapascal, and that shows that how robust our mixture is. So we don't have any problem with that. And also about the shear, we use the slant shear strength to kind of like represent the interlayer bonds. And this is a very effective method actually. And as you will see, anyway, we have lower interlayer bonds in our samples, which is technically because of the voids that SAP produce upon the release of water, of course, at later ages, okay? My previous results on SAP shows that over time, these voids will be filled, and it's not that effective. But anyway, what you see here is about 28 days. So we have a reduction in interlayer bonds. So that is also something we need to look at. And concluding remarks, this is a feasibility study. Your comments would be really appreciated because it's a continuation of a very big project that Dr. Zhou and I are working on. So SAP reduced the flowability at the first few minutes of open time, but later it was all right. SAP changed the printability parameters by delaying hydration, reducing the available water for flowability, okay? And SAP increased the chemical admixture content. I don't like it, not only because of costs. I don't like it because during the open time, SAP can manipulate the viscosity and the rheological properties of my mixture, and I don't like it. So there's something I have to work and see that how I can kind of like produce a more robust mixture. And SAP decreased extrudability right after mixing, but increase extrudability kind of like within that open time. And also SAP increase the deformation of at the lower layers. That's a problem. Controlling superplasticizer in the favor of, let's say, the viscosity. And this is an issue. But we know that, and our results, recent results show that SAP can inhibit the shrinkage due to the evaporation, but like I said, still, that is something that I'm concerned, reduce robustness of the mixture. Thank you very much. I just want to give the credit to Reese Sorgenfrey, our new PhD student that is working with Dr. Zhu, and Dr. Zhu that is already in this session.